real quickly. Not all of you may be familiar. In fact, probably most of you are not familiar with these Canopy sensors. So I'll start with what are these things? And they're things that look down at the crop from a moving fertilization machine and evaluate its appearance. And they measure the reflectance both in visible and near infrared wavelengths. And based on what they see, they're going to be taken into, the information's taken into a computer in the cab, and nitrogen rate is calculated. And then it directs a controller. And the controller in this particular case, it's an anhydrous ammonia applicator. And that white tank on the back is full of anhydrous ammonia. And it's going to be knifed into the soil, and there's a ball valve back there that opens and closes to change the fertilizer rate. So when those sensors see dark green corn, that ball valve closes down and puts on a low rate of fertilizer. And then when they see light green corn, which is going to be more nitrogen deficient and indicate less nitrogen coming available from the soil, it opens up and puts on a higher fertilizer rate. And it's doing that about every second. So every second it's diagnosing and changing what does this corn need in terms of nitrogen. Why do we need to do that? And I started off trying to figure out what was the optimal nitrogen fertilizer rate to put on corn. And the first thing I found was, hey, this changes a lot from one year to the next. And I also found it changed a lot from one field to another. And then we finally did research showing, hey, it's actually very different from one place to another within the same field. I'd love to be able to show you all that data, and I could spend my whole time doing that, but I'd never make it to the checkered flag. And so I'm going to have to skip over that part and hope you'll trust me. But as I already mentioned, the nitrogen status of the crop is visible. When it's dark green, that means it's got high nitrogen. When it's light green, it has low nitrogen. And that diagnosis of what the crop's nitrogen status is with the crop appearance is more accurate than anything else that I have been able to come up with, and in my evaluation, more accurate than anything anyone else has been able to come up with in terms of deciding how much to put and where to put it, and to handle the spatial variability as well. As Mike mentioned, optimal nitrogen rate is a key both to high yield and to minimizing the greenhouse impact of corn. And the high yield is part of the key to minimizing greenhouse impact of corn. So let's start with adaptation. What are we talking about adapting to? Well, first of all, nobody knows. We're looking at climate models where they predict what we're adapting to. We can talk about what we're already adapting to, and there is something to that. More spring rainfall in the Midwest. I think that's something that a number of the models are predicting. Also predicting more variability, that the extremes are going to be farther out. And, well, let's think about that a little. In 2008, the areas outlined in black had more than 16 inches of rain April through June. And that was during my career at the University of Missouri over the last 17 years. The biggest scale that I'd ever seen to have that kind of wetness occur in the Midwest in the Corn Belt. It covered probably more than half the Corn Belt. In fact, a great deal of it. Not here in Ohio, but a great deal of it. 2009, again, a lot of the Corn Belt, more than 16 inches of rain. 2010, a lot of the Corn Belt, more than 16 inches of rain. 2011, a lot of the Corn Belt, more than 16 inches of rain, April through June. Now, is this more spring rainfall or is this normal? And so I look back at rainfall records, maps like this, back to 1957. And what I found was that other springs this wet since 1957, well, from 57 through 89, that's 33 years, there weren't any that were as wet as those four in a row. There were none. And then in the 90s, there were three, 90, 93, and 98. 93 was the big flood year for the Mississippi and Missouri rivers. And 2004 was borderline. I wasn't sure whether to include it or not, but it had a pretty high spring rainfall. And then 8, 9, 10, and 11 were all in that category. So I think when you look at a 60, 55-year record like that and see that there was nothing like this in the first 33 years of it, and then it's happened 7 or 8 times since then, you think maybe there is something to this more spring rainfall. Well, what are the impacts of that? This is a picture that was taken in 2010 near Oskaloosa, Iowa. And remember I told you that dark green corn has high nitrogen and light green corn has low nitrogen? Well, we're looking at a lot of light green corn there where there's living corn, and there's places where it's drowned out entirely. And Another thing I'd like you to notice, it's highly variable within fields. You know, it's not, there's dark green and then there's light green, and they're all intertwined in some of these fields. And so the nitrogen status is highly spatially variable. And I've got hundreds of aerial photos up on my website, and if you want this, I think this presentation will be on the web, and you can go and find my website and find how to find the photo galleries. They're grouped by state and then by nearby town, and so you could look for something that's local. It's pretty much just Iowa, Illinois, and Missouri at this point, I think. Well, you know, it's one thing to say, okay, we've got nitrogen deficiency there. It's another thing to document it and come up with measurements and numbers. And I showed this particular picture during an extension meeting one year, and a guy came up to me afterwards and said, you know what? That's my field that you showed. I said, oh, I'm really sorry to hear that, but you wouldn't happen to have a yield map that you'd share, would you? And he did, and he'd been very cooperative. And so he gave me the yield map, and we didn't capture the whole field in the photo because I just had a pilot flying around doing a survey. But you can see that the dark green areas match with the red areas, meaning high yield. If you're used to looking at ones where green means high yield, you have to flip your thinking, because green and blue mean low yield in this yield map. But the yellow corn is green and blue in the yield map, and the darker green corn is yellow and orange in the yield map, and red. And it's not as dark as the corn in the neighboring fields. So even the darkest corn in this field is not as dark as the corn in the neighboring fields. Well, the darkest corn was about 170 bushels. The lightest was around 80, and there was a pretty strong relationship that the darker corn yielded more, and the lighter corn yielded less. It didn't have enough nitrogen. There was a lot of other factors that influenced yield too, so there was a lot of bounce around that line. Well, this was the average in the field was 125, and the best was 170. I think even the best was short because it was not as dark as neighboring fields. Probably could have been 190, but just assuming 170 was actually the top yield potential for this field in this year, he lost 45 bushels on average over that field. At 265 acres, that's about 12,000 bushels of corn, and at 375 a bushel, that's about $45,000. Fortunately for him, this was 2009, and corn was only $3.75 a bushel. It would have been, he would have lost $70,000 last year if he'd done the same thing. But really, that's not much consolation. So that's just a downscaled single field example that's kind of something your mind can grasp. When I say 2 billion bushels, you know, you can't really wrap your mind around that very easily. And that's over the whole corn belt. But I'm saying that that's what I think for those 4 years we lost in corn production that could have been produced with all the other factors that were in place, but that didn't get produced simply because of lack of nitrogen. I base that on eyeball interpretation of about 1,500 aerial photos a year for 3 of those years, and 2,000 miles of August windshield survey for 3 of those years. So it's not quantitative, it's my gut guess on each of those fields looking at them. How much did we lose there? And I totaled them very carefully by region in 2008 and 2009. I didn't do that in 10 and 11, but I feel like there's pretty good evidence right now, and we're working on analyzing more of the aerial photos to make it more quantitative, but that it's a tremendous economic loss. It's also a tremendous loss of opportunity to put carbon into the crop and into the soil. I calculated over the weekend that would represent about 168 million tons of carbon dioxide. How much of that is stably stored in the soil? Sasha said 6% during her talk, so that comes out to about 10 million tons stably stored in the soil. That if we had just had the nitrogen right, we would have 10 million more tons of carbon dioxide in our soils right now in the corn belt. But even more important, a lot of the nitrogen that went down early that got lost as nitrous oxide, and I think I figured something like 4 or 5% of the nitrogen lost went to nitrous oxide. That may be off, but that would be 32 million tons of carbon dioxide equivalent. It doesn't really compare to how much we burn up as gasoline, but every million tons helps. So why are sensors going to help this? Well, you've got to use them during the season. In season, nitrogen is delivered to the corn a lot more reliably than pre-plant nitrogen if it's a wet year. If it's a dry year, it doesn't really matter. The timing makes no difference. But when you get wet years, that pre-plant nitrogen is at risk of loss. Good rate diagnosis helps too. I'm going to share some results from an experiment that we've done in central Missouri. And we started in 2007. I call it the long-term nitrogen systems experiment, and I'm just showing you 2 out of the 8 systems that are in it. So it's not really long-term yet. We're in our 6th year, I guess, now. Last year we lost it due to hail, but for the first 4 years with our 140 pounds per acre planting, which would be our MRTN in Missouri, for those of you who know what that means, we made an average of 86 bushels per acre. And with sensor-based nitrogen, when the corn is knee high, we made an average of 142. That's 56 bushels more. And it's because the nitrogen was there in July and August when the crop needed it, and June. And with the pre-plant, a lot of it was gone. In 2007, they yielded the same. But in 2008, 9, and 10, the yield differences were enormous because of how wet it was. Okay, well, that's how sensors may help with adaptation to wet years. What about dry years? Well, we've got a dry year, don't we? And I happen to know that there were a number of people who, some were using sensors and some were not, but they were all planning on in-season application. They put a 70 to 100 pounds down before they planted of nitrogen, which is somewhere in the half to 2/3 of what they were planning to put down, and they were going to go and put more on, but at the time they were going to put more on, if it was anhydrous ammonia side dress, they probably went and did it anyway because that decision came quite a bit earlier. But there are more and more of these high clearance spinners that can put on nitrogen later, and people who were planning on using those, a number of them opted out and said, you know, with the soil moisture I have right now and the corn is a little over knee high and it's already rolling up, I don't think I'm going to go put that extra 70 pounds of nitrogen on. I'm just going to sit tight. This particular machine that's in the picture does have sensors mounted on the front of it, and one of our retailers custom built, you know, the boom so that they could fold them up and road it. But it can cover a lot of acres fast, and it also gives people an option to pull the plug and not put the nitrogen on and not spend that money and not put that nitrogen at risk in years when the odds that it's going to pay off are low. What about mitigation? Well, there's actually 3 ways that sensors can contribute to mitigation. One of them is if you reduce the fertilizer rate, you're automatically going to reduce the amount of carbon dioxide going into the atmosphere because a whole lot of carbon dioxide is released during the manufacture of nitrogen fertilizer. They burn natural gas to provide the energy and the hydrogen that goes to make ammonia, and if you're not burning that natural gas, you're not putting that carbon dioxide into the air. Second is if you increase the fertilizer rate and increase yield, you pull more carbon dioxide from the air. And some of that, in most cases, is going to be stably stored in the soil. Rob sent me a paper where it showed that it was not, but adding that into the literature I've already read, I'm still going to say in most cases, some proportion of it's stably stored in the soil. Maybe not all cases. And third, and probably most importantly, when they reduce the nitrogen rate, and especially when no yield loss occurs, nitrous oxide production is going to be reduced. You may remember that Mike showed you a schematic graph that when you put on more nitrogen than the crop needed, that the amount of nitrous oxide produced went up sharply. And when you cut back from what the crop needed, it didn't go down that much more. So if you're able to use sensors to diagnose areas where you don't need as much and cut back to just what the crop needs, you're coming down that steep part of that curve. So I'm going to show you a few numbers to evaluate what the mitigation potential might be. And these are going to be based on my own data. Had 55 on-farm sensor nitrogen demonstrations. And these were demonstrations where we did strip trials through the field. There'd be a strip of some size where the nitrogen rate was based on the sensor, and then a strip where the nitrogen rate was chosen by the farmer, applied with the same machine on the same day. So there's no timing effect, and a timing effect would have been big in some of these fields in some of these years. This is just rate. This is just the rate decision that those sensors are making compared to the rate chosen by the producer. It was published last year in Agronomy Journal, and on average over those 55 sites, we reduced nitrogen rate by 16 kilograms per hectare with sensors and increased yield by 110 kilograms per hectare. How does that come out in terms of the 3 mechanisms that I mentioned in terms of mitigation? Well, you can see by far the biggest effect is decreased N2O emissions. I used GRACE 2011, which is the reference that Rob sent me, and that has appeared in some of our other group discussions and publications. And the change in rate resulted in nearly 10 million tons of carbon dioxide equivalents that would be saved in terms of reduced emissions if you scale this up to the whole U.S. corn crop. The observations we saw in those 55 fields, you scale it up to the whole corn crop, and it comes to about 10 million tons per year. And the increased carbon dioxide uptake and reduced end production both come to between 1 and 2 million tons per year. So again, not nearly as large, but every million tons helps. And so I'll wrap up. I don't even have a white flag yet, but I'm going to go ahead. Adaptation. Less nitrogen loss and higher yield in wet springs. You know, that's largely a function of timing rather than the rate decision, but the timing is a crucial component of that. The nitrogen is still there in June and July when the crop needs it if you put it on later in a wet year. It may not still all be there. You can still get nitrogen loss with in-season applications, but the risk average is much lower. You've also got the flexibility to reduce nitrogen inputs in a dry year. On mitigation, you've got the nitrous oxide emissions, I think, are the key thing, both reducing the nitrogen rate in places where you didn't need as much nitrogen is a crucial part of it, but also not putting the nitrogen out there in a year where it turns really wet and having all that water and all that nitrogen there at the same time. That's when you get nitrous oxide produced, is when it's real wet. And so just by changing the timing, you reduce the vulnerability of loss as nitrous oxide. And then you've got reduced carbon dioxide emissions during nitrogen fertilizer production if you're not using as much and targeting it better. And also if you increase yield, you're going to sequester more carbon dioxide in the soil. So checkers,